Here are the steps for how to solve this demo problem using the Google Sheet attached. So let's read the question. In order to prepare for a new moon mission, NASA decides to launch a 15-kilogram monkey named Bobo to orbit 10 times 10 to the 5th, 1.0 times 10 to the 6th meters away from the moon. The moon has a mass of 7.30 times 10 to the 22nd kilograms. The universal gravitational constant, which is big G, is 6.67 times 10 to the negative 11th. How much force does the moon exert on Bobo? Wonderful. Okay, so we gotta find force. And we have this great formula, which is G times mass 1 times mass 2 divided by D squared. So mass 1, let's find mass 1. It doesn't matter whether the moon or Bobo is mass 1, but I'm going to decide it's Bobo. And we see here that Bobo is 15 kilograms. He's a 15-kilogram monkey. So mass 1 is 15 kilograms. Okay, now, if mass 1 is Bobo, mass 2 has to be the moon. So here this says the moon has a mass of 7.30 times 10 to the 22nd kilograms. So I'm going to write 7.30 times 10 to the 22nd. All right. The universal gravitational constant, G, is 6.67 times 10 to the negative 11th. So I can always put that in for G. And we're going to find the distance. So it doesn't say distance anywhere in here. But it does say that we're going to have Bobo orbit 1.0 times 10 to the 6 meters away from the moon. That's how far apart these two masses are. Bobo, mass 1, and the moon, mass 2, are 1.0 times 10 to the 6 meters apart from each other. I'm going to write 1.0 times 10 to the 6th. You might notice that's a million. Oh, and make sure you've added your units here. This is all important. This should be kilograms. Distance should be in meters. And the universal gravitational constant should be in kilograms times meters squared divided by seconds squared. And that. So we're off to a good start. Now we're going to find the force. Find the force. So to get the force, you're going to open up that other sheet, this sheet right here. And it should look like this when you open it up. It should have no numbers on it. And the forces are going to have all these divide by 0 errors because I put in a formula in here which is the same as this formula. So we're actually going to apply this formula for you. So we have to add mass 1 into this sheet. So let's go find mass 1. Here's mass 1. I'm going to put it in the sheet. I'm going to put it here under demo. So this is the demo row, and we're in the mass 1 column. So mass 1 is 15 kilograms. That's easy enough. And it's going to convert it to scientific notation. So this is the same as 15 kilograms scientific notation. You'll note that it's got this e plus 1 instead of times 10 to the positive 1. Just computers do this sometimes. Instead of writing out times 10 to the positive 1, they make it easier on themselves and try e to the exponent right here. So mass 2. All right, so it's 7.30 times 10 to the 22nd. And here's where it gets tricky. If you're going to use scientific notation, you have to actually type this equal sign in. So make sure you type that equal sign in right here. I've put the equal sign right there. So it's 7.2 or 7.3? 7.330 times 10 to the 22nd. And then it'll convert to computer scientific notation. That e in there. That's great. Now we've got to put in the distance. Our distance was 1.0 times 10 to the 6th. So we'll put in equals 1.0 times 10 to the 6th. And now we're going to add in our G constant, which is going to be 6.67 times 10 to the negative 11. And this should give you a value, but oh, and see, so this is where you can make that common error. I forgot to put an equal sign in front of this 6.67 times 10 to the negative 11th. The computer thinks it's a word, not a number. So I have to put an equal sign in here. And so I put this equal sign in here, and my force value has turned green. And that's because I've calculated it correctly. So if I put in the right numbers here, this will turn green. And you can see that it's correct. And so our force is 7.3 times 10 to the first newtons. And so we can write that in, and here's our force. We can write 7.3, it is 7.3, right? 7.3 times 10 to the first newtons. You could also write this, you could take this out of scientific notation if you wanted, it's a small enough number. It's going to be 73 newtons of force. So that's how much force the moon is exerting on Bobo. All right, excellent. So go ahead, you're going to answer these 3 questions below. So good luck, and as always, feel free to come by asynchronous time. I'd be happy to help you out.